Okay, some bigger molecules, covalent molecules, can have some more complicated oxidation states. In fact, they can even have the same type of element within them with different oxidation states. To illustrate this, I'm going to compare three compounds. I'm going to compare ethane, ethanol, and ethanoic acid, or acetic acid. So these are all common compounds we've heard of before. This is ethane. This would be a lot like natural gas or methane that we burn. This is ethanol. This is the alcohol that some people drink. And this is ethanoic acid that we more commonly know as vinegar. Okay, so let's look at the oxidation states, and we're going to compare this carbon and this carbon. This carbon isn't going to change in all these different examples, and this carbon is going to change. So here, this carbon has a effective nuclear charge of +4, or a root +4 charge, and he gets both of these electrons, both of these, both of these. The electronegativity of hydrogen is 2.1. The electronegativity of carbon is 2.5. So carbon wins all those battles and he gets -6. And then here, carbon is bonded to himself. So he gets one of these two electrons and he gets the other one. So he gets one more electron. And that carbon is in an oxidation state of +4, -7, so -3. So that's -3. If you look, this carbon is the exact same. And in fact, he's still -3 here. And he's still -3 here. So that carbon on the left, throughout the molecule, throughout all these changes, does not change its oxidation state at all. And that's how you find it. Now let's look, when we change it to ethanol, what happens to that other carbon's oxidation state. Here, this carbon is still getting credit for one of these electrons, 2 here, 2 here, but these shared electrons with oxygen, it does not get credit for because oxygen has an electronegativity of 3.5. So oxygen's electronegativity is higher, and thus oxygen will take those electrons effectively away from the carbon. That means that when considering its oxidation state, I still start with that root effective nuclear charge of +4. I get 1 electron from the shared bond, 4 electrons from the pairs that carbon sort of has control over, and then I don't get any from that shared pair of electrons. What that means then is this carbon has been oxidized. It has had an increase in its oxidation state. Instead of being -3, it is now up to -1. Let's see what happens when we oxidize it further. When we oxidize it further, now this carbon is bonded with oxygen twice, and oxygen, having that high electronegativity, will take responsibility for all of these electrons. That means that this carbon really only has a 1 out of 2 share associated with the other carbon that it's bonded to. It starts with an effective nuclear charge of +4. It has control over one of its electrons. It's lost the other, 6. And that leaves it in an oxidation state of +3. That's the highest oxidation state we're going to be able to get this carbon to without breaking the molecule up completely. So there's nothing for it. We have to do the Lewis structure to find the oxidation state here, especially because if we imagine trying to do any math to do this, we have 2 carbons here. Yes, they're both -3, so we could have done the math on that compound. We could have said carbon, 2 of them, plus 6 hydrogens, all at +1. So 6 times +1, 2 carbons, would have added to 0 because it's a neutral molecule, and 2 carbons plus 6 would be 0. And we would have been able to predict those carbons' oxidation states. But what would have happened if we'd tried to do that with this molecule? C2H5OH. 6 hydrogens at +1. And an oxygen at -2. And 2 carbons. Not equal, sorry, plus. And that has to all add to 0. So 2 carbon plus 6 from the hydrogens minus 2 from the oxygen would have predicted the carbon oxidation state at -2. But what's really going on here is we have one carbon whose oxidation state is -3 and the other one's who's -2. So really what this is predicting is the average of the oxidation state of carbon. It does show that it's changed, but it confuses the idea that one of them is changed by 2, and it makes it seem like they've both changed by 1. So we can't use the equations sometimes, especially with these organic molecules. We have to actually draw out the Lewis structure and look at the oxidation state of individual atoms as they change. So that's how you can do those Lewis structures to see what the oxidation states are.